Hi everyone, welcome back to the channel. I'm the GCSE science teacher. In today's video, we're going to talk about the Earth's atmosphere and how it's changed over time so we have the climate we currently do. I hope you find this video helpful, and if you do, let me know by giving it a big thumbs up, share it with someone else so they don't miss out, and please do also subscribe if you haven't already. Thank you so much to everyone who has. It's lovely to have you here. So let's get started. Now, this topic is part of the chemistry of the atmosphere topic, and you do need to know a bit more detail to this topic in terms of the greenhouse effect. You also need to know about different human impacts on climate change and global warming and the different things that humans have done over time that have actually really made a big impact, and what we're currently doing and what scientists are kind of advocating now for us to do. And we'll cover that in another video. But this one is all about the atmosphere itself on Earth and how it's changed from the beginning of time and the creation of Earth to current day period. So let's talk about it. What is the atmosphere, first of all? Now, when we think about the atmosphere, we often think of it as just a layer of gases, or we look up to the sky and we go, okay, the sky's there, and then we have space. But it's actually much more complex than that. So yes, it is a layer of gases based on temperature. And as you can see, there's lots of different layers. Scientists have actually categorized these based on the temperature and the gas composition. So the layer that we see, the lower part, and what we experience as our weather is what we call the troposphere. And just above that, we have the stratosphere, which has things like ozone, which is O3. And ozone's a really important gas because it actually protects our skin and our bodies by kind of absorbing UV radiation. Actually, there was a big problem many years ago with chemicals called CFCs, and these essentially were found in aerosols and hairsprays and even refrigerators, and also some fire extinguishers as well. And when they were sprayed, they would actually reduce the amount of ozone in the atmosphere, and this caused a big problem, because what happened was there was actually an Antarctic ozone hole, which meant there was kind of like a hole for the UV radiation from the sun to get into our atmosphere, and through it, I should say. And this could lead to problems like skin cancers and things like this, because obviously skin cancer forms from UV radiation as it ionizes our DNA. So yeah, it was kind of a problem until, the government and the people who were making these products, they actually stopped making them and stopped having them. These CFCs were no longer used, and now the process of the ozone layer repairing itself is actually underway, and it's a lot better than it used to be. But yeah, ozone is found there. We also have other gases as well. Interestingly enough, the world's record skydive happened at this state, really quite high up, outside of our normal layer, that troposphere. So that's the stratosphere. After this, we have the mesosphere, which again has a layer of gases, but this is an incredibly cold layer, minus 90 degrees Celsius. And just above that one, we have the thermosphere. And this is where the majority of UV and X-ray radiation is absorbed from the sun. And this is much hotter than, say, the mesosphere because of those reasons. And this is due to the gas composition. Now, I'm mentioning this because this is a really fundamental idea for the greenhouse effect, because the greenhouse effect essentially is when the sun's radiation is trapped by greenhouse gases like methane, carbon dioxide, water vapor. And those greenhouse gases essentially act as like a thick blanket trapping that sun's radiation and causes the temperature on Earth to rise. So it's an important concept to know that these gases actually play a vital role in temperature regulation on Earth. And then last, we have the exosphere, which is usually made up of just hydrogen and oxygen, and then we have outer space as well. So there's a lot of complex layers to this. This is not necessarily something you need to know a huge amount of detail for at GCSE, but it's worth knowing that the atmosphere is so much more than just one layer of gases. Now, we on Earth are situated within the Milky Way, our own galaxy, amongst other celestial bodies such as moons, planets, the sun, other stars as well. And as a result, we are in this solar system and in this galaxy, and we are orbiting around the sun, our star, because of the force of gravity. And gravity is a non contact force, as we know, it's measured in newtons. And as a result, this force keeps our orbit in place. However, it not just only does this, it actually helps our atmosphere form. So 4.6 billion years ago, our atmosphere began to form in those layers of gases, but it was very different to what it is now. And this has changed over time. And if we look back those many, many years ago, our atmosphere would have looked much more like Venus and Mars, because those are very close to the sun as well. So we can kind of interpret those atmospheres similarly to our own. However, due to the different processes on Earth and the different life that is found here, we now know our atmosphere has changed. So we're going to look at that now. So, during the Earth's early atmosphere, we know at the time there was little to no oxygen, and this is because there was really no life on Earth at the time. We say little to no because any forms of life that may have been there would have been extremely simple, would have been extremely primitive, but they may have been able to release some oxygen in some way. And this is additionally helped by the fact there was lots of carbon dioxide in the atmosphere. And we know that carbon dioxide, specifically the carbon element in CO2, is a very important element because it's found in every living organism on Earth. Plants, animals, bacteria, everything that's alive will have some form of carbon inside of it. And this is really helpful actually in techniques like carbon 14, carbon dating, to kind of see how old something is. But essentially, carbon tells you there is life there, which is why scientists are actually trying to find carbon in the universe as well. But yeah, like I said, in the early atmosphere, lots of carbon dioxide. Not much oxygen. There were some small amounts of ammonia and methane that were found there, and some nitrogen as well, but also some water vapor. And this was because of the amount of volcanoes and volcanic activity that was going on at the time. Remember, there was no real greenery there. You can see the difference here. When the water vapor was released from volcanoes, that would have condensed to help form oceans. So you can see that this development happened for a long period of time. In fact, this lasted for around 200 million years, which sounds like a very, very long time, but in context of 4.6 billion years, it's not a huge amount of time. But in addition, this is how our Earth and its environment looked at the time. However, after this period of time, the Earth's modern atmosphere began to develop and has now developed to what we know of as today's date. Okay, so what does it look like now? So the majority of gases found in the Earth's atmosphere is actually nitrogen at around 78%. Sometimes you'll be quoted about 80%. It's worth just knowing there's some discrepancies there, but for the most part, it's the most abundant gas. And the reason for this is because nitrogen is an incredibly stable gas, and it's incredibly stable, which means that it's not really involved in any chemical reactions. And as a result, it kind of just accumulated over time. It's not really gone anywhere, it just kind of stays as it is. In addition, though, we also have some other gases. So we know that oxygen levels specifically have increased quite dramatically from little to none to around 21%. And this is very substantial because of the effects of growing plants, greenery, algae, and essentially the process of photosynthesis. Without plants, we wouldn't have the oxygen we need for ourselves to live, but also as a food source. But more importantly, that oxygen is vital for pretty much every living thing. Remember, oxygen is really useful even for plants as well, for the process of respiration to break down glucose and release energy as well. So essentially, oxygen is very vital, and it's great that it's increased dramatically since the beginning. However, what has decreased over time? Well, one gas that's decreased considerably is carbon dioxide, also water vapor and noble gases. So although the noble gases and water vapor, we can kind of say, yeah, there's less of those, carbon dioxide is the one you need to know has decreased over the time. And this is because as the water vapor started to condense and form the oceans, carbon dioxide actually was dissolved in those oceans. It's what we call a carbon sink. So it absorbs that carbon dioxide and forms into the oceans as well. In addition to this, we have rocks. So sedimentary rocks specifically, like limestone, will actually capture some of that carbon dioxide as well. And limestone is often found near water, like oceans, and that can kind of contribute to the carbon sink situation. So it absorbs that carbon dioxide. In addition, remember, carbon dioxide is used by plants in photosynthesis. It combines with that water to form glucose and oxygen. So it's absorbed by plants and algae and other photosynthetic organisms as well. And then lastly, over the millions and millions and millions of years, or billions of years, that life has been existing on Earth, obviously there is an end point to life, and that would be death. And as a result, carbon has been found in fossil fuels. So, over billions of years, those fossil fuels have developed, and now we have essentially a great store of carbon. And that's why when we burn those particular fuels, we can release lots of energy from them. So these are all ways that carbon has actually decreased, carbon dioxide specifically has decreased in our modern atmosphere. Now, interestingly enough, this is not the end of the story because, as you know, the Earth is a very dynamic celestial body. It continuously changes based on the life and the human impact, especially that is going on. So, how it's currently changing is based on what we do as humans, the most dominant species on Earth, okay? And this leads nicely to the effects of the global greenhouse effect and how our climate has now started to be affected by what humans start to do. So, we're going to talk about that now. So, as you know, we have a layer of gases around the Earth that surround us called the atmosphere. And we also are orbiting the sun in our solar system, in our orbit. And the sun is able to emit lots of radiation, specifically electromagnetic radiation, in the form of UV radiation, ultraviolet light, visible light as well, infrared, X rays, all that kind of thing. And as a result, this radiation is absorbed by our atmosphere and the gases that are found there, specifically the greenhouse gases like methane, like carbon dioxide and water vapor. They absorb that light and radiation energy. And as a result, this heats up the Earth. Now, too much of these gases, too many of these greenhouse gases are now building up in our atmosphere because of the human effects. So, burning fossil fuels releases a lot of carbon dioxide. Increased cattle farming releases a lot of methane, as does landfills and increased pollution. Lots of these factors have actually increased the number of these gases in our atmosphere. So that means more heat is essentially trapped, more light energy, more electromagnetic radiation is trapped, more UV is trapped. And this causes an increase in the temperature on Earth. So that's why we call it global warming, because the world, the globe, is actually warming up as a result. And this has, loads of effects. So things like increased pollution for one, but also the effects of drought or melting ice caps and rising sea levels. So it has a big knock-on effect. Now, by no means am I saying that this is an absolute big problem by having greenhouse gases in the atmosphere. We do want some small quantities to maintain the temperature on Earth. We do need it because without any greenhouse gases, it actually would cause something like an ice age because we'd have a very cold planet. So we do need some heat. We do need some of the radiation to be trapped. But the problem is too much of it is being trapped. Now, at the time, like I said, some of this radiation is being trapped. Some of it gets emitted back into space and just transfers straight away out of it, but most of it is absorbed. And this is what we call the greenhouse effect. And that's it from me today. I've been the GCSE science teacher and you have been curious. If you did enjoy this video, let me know by giving it a thumbs up, share it with someone else, and do subscribe. If you'd like more revision resources from me for either biology, chemistry, or physics GCSE, feel free to, like I said, join our community, subscribe, but also you can find some more videos and playlists on the side here. And also I have an Instagram and TikTok. Everything is at the GCSE science teacher. I do cover lots of revision. So if you have any requests or specific content you would like to cover, feel free to let me know in the comment section and I'd love to get back to you. It's always good to hear what you guys have to say. Thank you so much for your time and support. Have a great day and I will catch you in the next one. Bye.